Hello everyone. I'm going to be talking about one of the commonly requested topics, which is on AM-GM. If you have requested for me to explain AM-GM, probably you have searched, you have asked ChatGPT, you have got some idea of what AM-GM says, which is, well, this. This is what AM-GM says. Now, I'm not about to invent a new version of AM-GM in this video, but I am going to agree that this is not the most helpful thing in the world if, let's say, that you were given this statement and then a list of 15 exercises, whether that be from a textbook or from your school teacher or even from me. I don't think you're going to understand AM-GM very well if that's all you get. Now, certainly I want to just explain the name first, which is that AM is the arithmetic mean and GM is the geometric mean. Now, these are just the names of two quantities, and AM-GM compares them. This is the arithmetic mean. This is the geometric mean. The arithmetic mean is the usual average, which is often when we say mean, median, and mode, mean is referring to the arithmetic mean. The geometric mean is calculated by multiplying together a bunch of things and then taking the root. How many things is up to you, but what this statement is saying is that if I take a bunch of quantities that are positive, so that the root will always make sense, I toss it in, then this will be true. For example, if I take the numbers x1 is 1, x2 equals to 4, the arithmetic mean is 1 plus 4 over 2 is 2.5, and the geometric mean is square root of 1 times 4, which is 2. So indeed, the statement that the arithmetic mean is greater than or equal to the geometric mean is satisfied in this one example. To just make sure that the name and the definition sticks around in our mind a little bit longer, we can also highlight the fact that these are all forms of measuring averages. These are all forms of measuring averages. And so if let's say that you wanted to get mean, median, and mode, they are also different forms of getting a meaningful average. However, the one thing that we would agree on is if I had a list of numbers 10, 10, 10, 10, 10, 10, 10, it had better be the case that any average of 10, 10, 10, 10, 10, 10, and 10 had better be 10. Otherwise, your understanding of average is complete nonsense. So accordingly, the arithmetic mean of 7 copies of 10 would just be 10 plus 10 plus 10 plus 10 plus 10 plus 10 plus 10 divided by 7, and that is 10. The geometric mean is if you multiply 7 copies of 10 together, how do I get back to 10? I should take the 7th root, so it makes sense why your nth root shows up. Very often, and I'm also guilty of this because of the fact that I cannot assume you know nothing about AM-GM. I will just go through this introduction at the start of a lesson, and then we'll say, okay, let's do some questions. Because there will be maybe half the class that already knows AM-GM and are already rushing to look at some interesting problems. So when we stop here, what is often lost is, well, quite a lot of things. There are many different ways in which you can fail to properly understand AM-GM or fail to properly link it to many other things that we know. And so that's what I want to do in the remainder of this video. stage 0 in your understanding of AM-GM is that it's an assertion. Now, the problem that we have is that we tend to just use the word solve a question, solve a problem too liberally. And AM-GM is not something to solve. Now, when I ask you to solve, let's say, x squared is greater than or equals to 2x plus 1. This means, tell me when this is true. So you can solve this in various ways. For example, if let's say that you use the quadratic formula, you can say that your roots are 1 plus or minus square root 2, and so you say that, all right, so this is true when x is more than 1 plus root 2 or less than or equal to 1 minus root 2. Now, this is not what we mean by here's an inequality, because the AM-GM inequality is always true. So we are not supposed to solve it, we are supposed to use it. For example, I could say that x squared is always greater than or equal to 2x minus 1. Now, I'm not saying solve this, I'm saying that this is true, period. Always. Of course, in this case here, it is not because of AM-GM that it's true. It's true because if you were to push it to the other side, this is x minus 1 squared. So this is saying that it is true all the time because a square cannot be negative. Now, technically, if you were to say solve this, the answer to this is all x. So that's not really what it is meant to be used for. Now, if I know that this is true, x squared is greater than or equals to 2x minus 1, this means that I could say that, that means that it would be true that if I let x equals to square root 5, 5 is greater than or equals to 2 square root 5 minus 1. If let's say that I let x equal to 1 over 17, it's true that 1 over 17 is greater than 2 times 1 over 17 minus 1. So 1 over 17 squared. And this is to be used. Unfortunately, whenever you see the topic inequalities in school or in a textbook, it may not be clear whether they are teaching you to solve inequalities or use inequalities. And those are two very different topics. So this is using the inequality. To get information. That's what AM-GM is doing. It is not to solve an inequality. So if let's say that the next time you see some inequality like, x cubed is greater than or equals to 3x squared minus 4 plus 2 over x or something. No, AM-GM is not supposed to be used to solve this. That's a different topic entirely. Don't mix them up. Now, this is the first, or in fact, the 0th thing to understand. Okay, so AM-GM is just telling you that here are two quantities. It turns out that magically, the first quantity is always bigger than the second quantity, meaning that these two different ways of calculating average, the first one's always bigger. This makes more sense than you think. My go-to example for why does this make more sense than you think is to appeal to something that, well, in maybe primary 4, primary 5, or primary 6, your math teacher would just tell you that, suppose that I have a rectangle with perimeter equal to, let's say, 40. Now, what is the biggest possible area? Now, surely if you were to look at this, you would say that, oh, that is obvious, I want a square. So if it were a square, then how do you get a square? Well, perimeter is 40, means 10 by 10. And if let's say now I say, all right, how about if you flip it around and say that I have a rectangle with area equal to, let's say, 64. And I ask you what is the smallest possible perimeter. Now again, you would tell me that's very obvious. It's still a square. So still a square, 8 by 8. And your answer is your perimeter equals to 4 times 8 equals to 32 should be the smallest. Why is it that obvious? Well, it is something that for a long time, I don't think we had to challenge this. And so if you have said that this is obvious, then let's look at a numerical example. If I were to tell you that, okay, here, let's change it to xy equals to 64. What is the minimum possible value of 2 times x plus y? Or you know what, just forget the 2, there's the x plus y. Well, that's the same question, right? So we are saying that it is just going to be 8 plus 8 equals 16, because if you were to spread them out, so that is actually the thing in the thumbnail. If you were to spread them out, essentially, if you were to take the 8 and you go down to 8 minus a, and you take this 8 and you go up to 8 plus a, then 8 minus a, 8 plus a, is 64 minus a squared. That's smaller. In other words, in order to get to 64, I need to take the 8 plus a and move it up a little more. And so the total is going to get even a bit bigger. Okay, so if now I just change 64 to the letter a. Or you know what? I'll use p for product. If xy equals to p, what is the minimum possible x plus y? Well, by now you have been conditioned, and I'm sure you can say this is obvious. You would say that x equals to y equals to the square root of p, and so x plus y is at least 2 square root p. But what do you know? This is just saying that x plus y is greater than or equals to 2xy, and if you move the 2 downwards, that's AM-GM. So this makes sense. And of course, if you were to take more than 2 numbers, and I ask you for the minimum, you will say that this is at least now 3 times if they were all the cube root. They're all the same. And so you end up with x plus y plus z over 3 is greater than or equals to the cube root of p, which is xyz. This is 3 variable AM-GM, and so on. In other words, the statement made by AM-GM is just a more technical looking and fancy way of saying something that we said was obvious some time ago. I want to say a bit more about these 2 and 3 variable examples though, because you may not quite have realized to what extent these appear everywhere. So let's talk about x and y. The first thing to point out about this is that this is the same as if you complete the square, square root x minus square root y squared is greater than or equals to 0, which is obviously true. In other words, this is just a rearrangement of one of our algebraic identities. Now, here's something that is an interesting problem in the SMO. For what, let's say, C, does there exist x and y such that x plus y equals to, let's say, 2c minus 8, and xy is equal to c squared minus 3c minus 9. Now, at first glance, you might say that, what does this have to do with AM-GM? And then you will say, oh wait, that's x plus y and xy, right? Well, indeed it is x plus y and xy. So you might think, I want to say therefore that, okay, by AM-GM, x plus y over 2 is greater than or equal to square root of c squared minus 3c minus 9. There's, however, a bit of a problem, because what happens if that's a negative? Now, when we say that exists xy, I didn't say positive. So this technically only works for positive, so we would not want to write this down in this way. We would want instead to make use of Vieta's. Our Vieta's formulas tells us that x and y are roots of this quadratic, which I will use c as the variable. Right, sum of roots, product of roots. Since those are the sum and product of roots, then I've got a quadratic. I know how to handle quadratics. If x and y must exist, I didn't say they must be distinct, so it just means that the discriminant, the b squared minus 4ac, although this c is of course not the same as that c, must be greater than or equals to 0. Okay, so let's put this in. Expand it. And so you get c is less than or equals to 5. Now, then we can look at this and say, well, what does it have to do with AM-GM? You just said AM-GM does not work. Well, not so fast. The discriminant is this squared minus 4 times that. In other words, the discriminant is x plus y squared minus 4xy. Now, do you realize that's just what you get from squaring AM-GM? So AM-GM only works for positives. But if you were to take powers of it, it can work for negatives as well, subject to enough conditions, of course. So in this case here, this is for xy positive, but this is for all reals xy. So you understand therefore that AM-GM actually does apply as well. It's just that you needed to use the squared version, not the square root version, because then that would not give you necessarily a defined quantity. Alright, now, with this being said, it is true therefore that the two variable case does not always require AM-GM. But it has kind of been there all along. Meaning that, for instance, if we took one of many examples where I ask you, for example, the maximum value of 5 minus x times x plus 3. Previously, we would have said complete the square. But now, if I want it to be maximized, these two sum to 8. Obviously, I don't want to maximize it by making something negative, so I can assume they're both positive, and using just the common sense I said just now, if they sum to 8, then the maximum would be when they're both 4, when x equals to 1. That is AM-GM, because AM-GM applied to these two guys says this. So this is the AM-GM statement, but really, so is this. It's just that it made more common sense when you looked at it that way. And from that perspective, you can say that, you know what, actually completing the square, AM-GM, our discriminant, are effectively all the same thing, for two variables at least. When we take it and push it a little bit up to 3 variables. For 3 variables, all is not lost. For our algebraic identities, they still can help us to deal with x, y, and z. Specifically, our identity x cubed plus y cubed plus z cubed minus 3xyz can be factored as in the thumbnail. This is our identity that some of us would have seen before in various SMO or AMC problems. How does this relate to AM-GM? Well, simple. If your x, y, and z are positive, then right hand side is clearly positive. So, well, greater than or equals to 0, that is. So, the left hand side is greater than or equals to 0, which means that x cubed plus y cubed plus z cubed minus 3xyz is greater than or equals to 0. This, my friends, is also AM-GM, because if you apply AM-GM to these 3 guys, the arithmetic mean, the geometric mean, lo and behold, it says the same thing. In other words, AM-GM is just doing a more extended job. It can handle more than 3 variables. Even when it handles more than 3 variables, it makes perfect sense. Because the logic is just to get a big product, make all of them the same. To get a small sum, given a fixed product, make all of them the same. The reverse direction, of course, doesn't make sense, because if I ask you what is the smallest possible area, that doesn't make any sense. I mean, just make one of them extremely narrow. So likewise, in each of these cases, it doesn't make sense to ask how small can I make 3xyz given x cubed plus y cubed plus z cubed. But it makes sense to say how small can I make x cubed plus y cubed plus z cubed given xyz. Okay, so now that we understand what AM-GM is saying, why it makes sense, let's get to some examples that tell us what AM-GM does in an Olympiad context, which is most of the time, it optimizes stuff. Now, it optimizes stuff, meaning that it tells you how to make things big or small, but usually not both, because as we said, one direction is usually pretty silly. Only one direction is not so clear. How does it optimize stuff? Well, AM-GM is sum over n is greater than or equals to the nth root of the product. So it tells you two things in words. It tells you the sum is at least n times of the geometric mean if this is fixed. Meaning, if there's a fixed product, the geometric mean is actually a number. The product is at most the arithmetic mean to the power of n if there's a fixed sum. You have the sum, you have the product. Therefore, if the question asks you, what is the minimum value of some sum? Or what is the maximum possible product? Then you will use AM-GM to hopefully get your answer. For example, right, the most straightforward sum situation is if I gave you x plus 1 over x, where x is greater than 0. Now this has a product of 1, so it has a sum that is at least 2 times of the geometric mean, which is also 1. So it's at least 2. If I now had 2x plus 1 over x, I would then say that it's greater than or equals to 2 times 2x times 1 over x, which means it is 2 square root 2. If I've got more things, let's say I have got x squared plus x plus 1 over x cubed. Now this is going to be greater than or equals to 3 times of the geometric mean, which is 3. On the flip side, it can tell me what is the minimum possible sum. Sorry, what is the maximum possible product given the sum. So if let's say that I have got x plus 5, 15 minus x, as with the example we saw just now, the product is at most the arithmetic mean to the power of n. So at most 100. If I've got, let's say, you know what, let's tweak the numbers a little. Just so they look a bit nice. the three things, it still has a fixed sum. You add them instead of multiplying them. The arithmetic mean cubed because there are three things. And so this is going to be 11 cubed. Sorry, I can't count. 13 cubed. Which is 2197. So fundamentally, it optimizes stuff that have a fixed either sum or product. You can use that to know the minimum possible sum or the maximum possible product given the other thing. Now, of course, it can work with more than one variable. It can also work if they tell you something. So if I were to tell you, by the way, x times y is equal to 16 and ask you for the maximum value of 4x plus y. That will be wrong because it should not be asking you for the maximum. The maximum is infinite. Just make x really big and y really small. Minimum value of 4x plus y given that they are positive. This is still two things that have a fixed product. So their arithmetic mean will be greater than the geometric mean. This is the sum. So it is greater than or equals to 2 times of the geometric mean, which is a fixed value. So I still know that this is going to work. And you can have a whole long list of things. If let's say that I've got A, B, C, D, E equals to 120, and then now I ask you for, okay, A plus 2B plus 3C plus 4D plus 5E, and ask you what is the minimum value of this. You can say that, all right, I am just going to say that they have a fixed product. So it's greater than or equals to now 5 things. So 5 times of the geometric mean, which is going to be just some weird value. So whatever that is will be the minimum value of A plus 2B plus 3C plus 4D plus 5E. That is essentially how AM-GM is used. But you might ask, okay, is AM-GM telling me this is the minimum value, or is it just telling me that this may be the minimum value? Right? Because AM-GM just told me this. And if you were to think about it, at the very start, we just saw a numerical example where I just said, you know what, if I use just 1 and 4, 2.5 is more than 2. But 2.5 is certainly not equal to 2, right? So what makes me think that they will be the same? That smallest value is actually the smallest value? That's what equality holds is saying. Equality holds is saying that, well, whatever you got as your potential minimum, that requires that all the things you put into your AM-GM inequality should be the same. If they can be the same, then you win, which is what we were trying to do when we had the square and the rectangle just now. We tried to make them the same. So, well, let's look at our examples a bit more closely. Now, when I said that 2x plus 1 over x is greater than or equals to square root 2, when is it equal to 2 square root 2? Your equality case is when 2x equals to 1 over x, which means x squared is half, x is 1 over root 2. That's where the minimum occurs. If I had the example here where I had xy equals to 16 and I want the minimum value of 4x plus y. Then it just means that I should have 4x equals to y at that minimum value. Which, of course, if you say, when does it happen? Well, simple, right? If 4x plus y equals to 16, if both sides are the same, then they should be 8. So x equals to 2, y equals to 8 is how we manage to make them the same. Let's look at an example. Suppose that I have got x squared plus 2x plus 4 over x cubed. Now, what would you say is AM-GM's answer if I ask you what is the minimum value of this? Well, you might say that x squared plus 2x plus 4 over x cubed is we are experts by now, right? So this one, the x squared, the x and the x cubed cancels off. It's a fixed product, so very good. It's a value 6. When is it 6? When each of those three things is equal to 2. Okay, that's not quite right, is it? Yep, that's not going too well. That's not ever happening. Is AM-GM wrong? No. It just said it is greater than or equals to 6. That does not mean that it can be equal to 6. So in all the things that we apply AM-GM to, the statement of AM-GM is going to always be that, oh, here's a comparison. Can it actually happen? I don't know. You deal with that yourself. You can just see. Does it work? Does it not work? It depends. Now, it tells you how stuff were optimized also means that this is sort of the positive example. This is the negative example. Negative in the sense that it helps you to realize that AM-GM applied in this way did not work. And to be fair, if you're saying, how does AM-GM then work for this question? I don't know if it works nicely because not always is the value of x going to be nice. I just, on a whim, just toss together this example. It's not guaranteed that every single combination will have a nice minimum value. Some of them are just going to have weird irrational stuff. But in the SMO or in any competition, there is also another reason why you want to talk about this, how stuff were optimized. The reason is that there's a second way to ask the question. The second way to ask the question is if I were to just tell you something that, x cubed plus y cubed plus z cubed is equal to 81. And then xyz is equal to 27. And then find x squared plus y squared plus z squared. Again, assuming positive. If you try to use your algebraic identities to get x squared plus y squared plus z squared, you're going to be here for a while. What AM-GM also does is that it is kind of telling you two quantities that only meet at one very, very specific place. If I were to say, or you were to say that you met the president recently, I would assume that you must have seen the president at the National Day Parade. Because where else would you have seen our president? So there are very few places where you would just meet the president, and therefore the fact that you met kind of narrows down your location. Similarly, if these two can be related by AM-GM, we saw a while ago, this tells you that if they meet, which in this question they do, the three things that went into AM-GM must have been the same, which of course is that it is equal to 3. Now this is perhaps a slightly more obvious example, but there can be more subtle ways in which this is snuck in. For instance, if let's say that we were to use x cubed plus 2y cubed plus, let's use some other example, maybe x squared plus 4y cubed plus, as you can see, not that easy to set a question, right? Now I can't spell xyz. Okay, let's do this. Let's use x cubed plus 2y cubed plus 4z cubed equals to 81 instead. And now I have xyz is equal to 27 over 2. This is actually the same thing. Just trying to do substitutions in my head to make the numbers nice-ish, but not as obvious. And let's say I ask you for x cubed plus y cubed plus z cubed. When you see something like this, it is often the case in an Olympiad that to get a value that doesn't look so nice, like x cubed plus y cubed plus z cubed doesn't really come out from this. It's just an answer extraction where you should be able to find x, y, and z. But how do I find x, y, z from two equations, three unknowns? The likely situation is that it is just a special instance of an inequalities equality case. If we use AM-GM here, we realize that these two are equal to each other because now both of these are equal to 27. What are x, y, z then? So if you were to take what AM-GM has told us, we can conclude that, okay, if you're telling me the geometric mean is 27, the equality case is that these things, not x, y, and z, but the things that you put into AM-GM are equal. And so y and z themselves are pretty ugly. X is 3, but y is 3 over cube root 2, z is 3 over cube root 4. Of course, you could calculate this, which is not the most important aspect. AM-GM, as an inequality, tells you that these two things should rarely be able to meet. hence allowing us to make this conclusion. Now, thus far, I have been curating the values pretty deliberately so that when we talked about a product, the geometric mean, the average, so far things have been working out pretty nicely. But here's where we can upgrade AM-GM a little. And the way we upgrade it is to weighted AM-GM. Now, currently, a lot of you have a GPA style system in your school, right? So based on a certain number of subjects, they will average out your score. Kind of. Wouldn't it be nice if, let's say, that you could put a triple weight on your best subject, like math, I hope, and you could put maybe like a 1/3 weight on your least favorite subject, maybe, I don't know, geography, literature, bio, whatever you like the least. Wouldn't it be nice if you don't just average it, but you could say, I want more of this and I want less of that? Try proposing that to your teacher. I don't think you're very likely to succeed. But in the world of AM-GM, we can. Now, here's an example. Very simple. If let's say that now I asked you for the maximum value instead of what we had earlier, which is, let's say, x plus 5, 15 minus x, 2x plus 9, 15 minus x, 15 minus x. Let's say that I ask you for the maximum of x plus 3, 10 minus 2x. Do these two have a fixed sum? No. But this is a bit contrived, right? Because actually it's just you factor out a 2. And so now you would be able to use AM-GM. Okay, so then if this is a bit contrived, you say, how about if I ask you for the maximum of x squared times 9 minus 2x? Again, all of this with x more than 0. And okay, I should add x is more than 0 and 9 minus 2x also is positive. Otherwise, you could just let x go to negative infinity. Well, sorry. I don't need that, right? X is more than 0 is enough. Okay, so how would you get the maximum value of x squared times 9 minus 2x? Now, if you were to use AM-GM naively and say that, hey, these are the two guys, I'm going to conclude that it is less than x squared plus 9 minus 2x over 2 squared, which is true but pretty useless. However, you are able to make things appear more, if you want them to, by, let's say, chopping it up into x and say, you know what? I don't have two things. I have three things. So with x, and 9 minus 2x, I have got this statement here, which gives me the value I want. Now, the same thing applies if you have got, let's say, I want the minimum of x squared plus 1 over x. Again, with positive x. Now, if I want the minimum possible value of x squared plus 1 over x, and you tried to use AM-GM, this is a sum, you will get the latest iteration of true but useless, because is greater than or equals to 2 square root x, but 2 square root x can move around, so how do I know what the minimum value actually is? So what you can do is to say that I want them to cancel out. I want the product to be nice. For the product to be nice, I need to be able to get rid of the x squared, and this is only x. So let's make one more. And when you say one more, you can just slice it into two. Now the weighted AM-GM, therefore, it's just like, imagine that your math paper can count for 2 times or 3 times. You'll be happy about that. That does not mean you take 3 math papers. You're saying that if I could just count it twice, that'd be great. For AM-GM, you can. You can make it count twice in terms of how you chop things up before putting them into the AM-GM inequality. Now, notice just like a moment ago that this is a pretty weird value, and the reason why it is weird is that the equality case is when x squared equals to 1 over 2x. So x is 1 over cube root 2. That's why you won't be able to guess it at all. It's a pretty random number, wouldn't you think? And yet, AM-GM is going to give you both the answer, what is the minimum value, as well as how you get it. So this is going to be something that you can find to be pretty entertaining. It's pretty entertaining because you can essentially do all kinds of things. And this is also for proving. If let's say, for example, I've got x to the power of 4 plus y squared. And I want to establish an identity for it that is, this is greater than or equals to, let's say, something times xy to the power of something. Let's say that this is what I'm trying to establish. Now, if I'm trying to establish this, effectively, I want to make sure that my x and y appear in equal weights. You know what? I'm just going to change this to cube because it looks too similar to just now. And so if I want to make x and y appear in equal weights, x has a 4, y has a 3. So to compensate, I need 3 of these and 4 of these to make them both the same. So I just do that. And I can say that it is 3 copies of 1/3 x to the 4 and 4 copies of 1/4 y cubed. So this is not yet an inequality, so just to avoid confusion, this is equal. Now I've got 7 things. 3 of this, 4 of that, which is going to give me some fairly weird number to be fair. But yeah, that would be a statement that you can get. You can configure it to give you whatever kinds of things you want. Now, this allows us to be able to get one last piece of intuition, which is going to kind of, a bit later on, perhaps if this series continues, lead to the Merhead's inequality. The intuition is that because of the fact that your AM-GM, the arithmetic mean is made up of separate terms, you can chop them up how you want, and then the geometric mean is basically all of them just get shoved under a root. It means that you will be able to tell to some extent which ones are bigger. which is that there must be the same number of things on both sides, right? You see that here, there were 3 things and 4 things leading to 7 things. Right? So the same number of things on both sides. Now I keep saying things because they can be values, they can be polynomials, they can be roots, they can be anything. The same number of things on both sides. The more mixed up one is going to be smaller than the less mixed up part. Now this is a reference to the final thing on our thumbnail that I have not addressed, which is the second law of thermodynamics. The second law of thermodynamics talks about reversible and irreversible processes, and basically it is summarized as things get more random. Things move in the direction of more randomness. And this is so-called automatic, and it doesn't go in the direction of being less random, or rather, it needs an input of energy to do that. For example, if let's say that we are in Singapore and Singapore is always hot. Now, suppose that the average temperature in Singapore at some point is, let's say, 29 degrees. Now, you are in the room and the outside, let's say, if they are both 29 degrees, this is the normal state of affairs. Of course, it would not be a very pleasant state of affairs. You will say that, no, this is really warm. And so you turn on the aircon, and when you turn on the aircon, it means that you are trying to drive some of the heat out, right? So that, okay, now I have this pleasant 25 degrees. Our government would like us to have a 25-degree temperature so that we use less energy. Because we still use energy in order to push a little bit of out. Obviously, your room is more smaller than the surrounding, so maybe that will cause it that aircon compresses, blows out some hot air, and then in the rough vicinity of it, it becomes, let's say, 31 degrees. This, therefore, is so-called something that is more desirable. But this is sort of the equilibrium in a way that will make your science teacher vomit. Basically, this is the second law of thermodynamics. And this is also how AM-GM works. It means that if you were to look at, let's say I've got x and y here. Now I have got x squared y and xy squared. AM-GM is basically telling you that because the geometric mean means you throw some stuff in and you mix it up, you can eyeball it and say probably this is true. Meaning that if you see the same kind of things rearranged, so you see that there are still 3 x's, right? It's x squared and x. There are still 3 y's. Obviously, I would not be comparing x cubed plus y cubed to, let's say, if I've just got x plus y squared. I mean, I can't compare which is more mixed up. Those are 2 different things. Comparison is referring to cases where they have the same amount of things. I'll be more rigorous about this in a future video, but use this to guide you. Now, the proof of something like this is just by weighted AM-GM. X cubed, y cubed, x squared, y. How do I show the left side is bigger than the right side? X squared y is 2 parts x, 1 part y. And the reverse if you want xy squared. If you add them up, which of course gives you this. This is a really useful intuition to have, because if you were doing just some kinds of problems, you may find that it is a bit difficult to like explain where did the guy think of this thing from. You're like, how did he come up with this? But if you have the right intuition, it's not that bad. So as an example, let me just, so suppose that a plus b plus c is equal to what? I think I need more space to write this. Now, this is a typical example of an SMO round 2 kind of problem. Not the hardest one in the world, but an example nonetheless. Now, if I can come out with it, this is unscripted as usual. So if I can come out with it like on the fly while talking, you know it's not meant to be a very long solution. Okay, what do you think I'm about to write down there? It'll be 3. Okay, so what I'm trying to say about this is that once you have this idea of AM-GM, AM-GM doesn't work in the sense of you must toss everything in every time. As you have seen here, we just tossed in some of it. How AM-GM works is that if I want to show that this is greater than or equals to 3, I want to just make the left-hand side gradually smaller as incrementally as possible until it reaches 3. It should be incremental. Otherwise, if let's say you did something and whoops, the left-hand side is bigger than something which actually can be equal to 1. And because you shrunk it too much. Let's be incremental. So if you want to do it incrementally, oops, actually I think I have the direction wrong. So incrementally larger. Now, to make the left-hand side incrementally larger, basically means that you are going to look at this because it is pointing the wrong way. I don't want to view this thing as a sum of 3 things, because if you were a sum of 3 things, it should be more than something geometric mean related. Furthermore, I don't really want to multiply this. Too horrible. To make the left-hand side incrementally larger, it means that either I will make the numerator a bit bigger. How do I make a be a bit bigger? Do I want it to be that a plus b squared over 4? I don't see why that's useful. So numerator up or denominator down. To make the denominator go down, you will realize that you must start from something big. And in the denominator, ABC is small because it's the most mixed up. But the cubes are the least mixed up. They are just their own A's on their own, B's on their own, C's on their own. They have potential to be pushed down. And you can use this. So you need to be able to make this kind of transition, even if it's not proving this question here. It is useful to be able to say that AM-GM gives me a feeling this is correct. And so a cubed plus b cubed, I can make the denominator a bit smaller because these factors, and this becomes 1. Okay, because a plus b plus c equals to 1 in the question that I've set up in this way. That is how we can use AM-GM on any part of an inequality to be shown, and thereby we are able to handle even a huge host of problems that you see in SMO round 2 or even questions in the IMO or other places. There are more things to say, but I think the video has gone long enough. So this is AM-GM. When we understand it and we also understand how we approach inequalities, the same logic applies to all the rest of the things you may or may not be familiar with, your Cauchy-Schwarz, your rearrangement inequality, your Jensen's inequality, and so on and so forth. So we'll continue to look at some more things on inequalities, but I hope this lays a good foundation. Let me know in the comments if you have any questions, and otherwise, see you again whenever the next part is ready.